In Chem Inquiry 4, Part 1, Question 1, you're asked to look through a discovery slide at a point of light and see if this thing is acting like a diffraction grating, which means will it produce a rainbow. So we've got our camera focused on a bright white light, and here's that slide sliding through different patterns. I hope that you can see the rainbow. So for part 1, we're going to look at the effect of shining a laser. In this case, you can see we've got a green laser. It's shining through what's called the discovery slide, which is just a photographic slide that has 8 different patterns on it. You want to look what happens when light shines through these different patterns. What pattern will it make far away on the screen, called the diffraction pattern. So let's look over here, and you can see that there's a reproduced image of the different patterns that are actually on that slide, and that's in your lab manual. And then one of the things you have to record is the wavelength of red and green laser light that we'll use throughout this experiment. So put that in your data table. And now we're going to take a look at what happens when we change the pattern that we shine the laser light through. In just this case, we're using a green laser, but the same thing happens with other colors. And so the first one we're shining it through right now is pattern B. So that is the pattern of spots that are made by shining a laser light through a set of horizontal lines on the slide. And next I'm going to move this so that the laser light goes through pattern A, which is a set of horizontal lines. So the green spots on the screen are what happens when you shine that laser light through a set of vertical lines on a slide. And now I'm going to move it back to pattern F, which is a sort of an intersection of both horizontal and vertical lines. And that is what you see in pattern F. So kind of think about what you're looking at in pattern F and how that is related to the patterns made through B and A. And that's the data that you record on the first page of the data sheet. This is the experimental setup for Chem Inquiry number 4. And so this is just a general overview of the overall apparatus we're going to use. And now I'm going to pan through and take a look at each component in more detail. We'll make some measurements. You'll record the data and do the calculations later in the experiment. So let's start out. One of the first things is the light source, and that's a little pen laser. This one happens to be red. So the wavelength for the red laser is 635 nanometers. And that is shining through a little slide, photographic slide that has little lines ruled on it that are too closely spaced for you to see with the naked eye. And we're going to try and figure out what is the distance D between those little lines on the slide. And so right now that laser is shining through a pattern of lines, and it's making a diffraction pattern way over here on the whiteboard. And so one of the other pieces of information we need to know when we make this measurement is the distance we are away from the screen or the whiteboard where the pattern is back to the slide. Not the distance to the laser, that doesn't matter. It's the distance from where the interaction of the light with the pattern happens, and that's on the slide. So if we look at this, we're lined this one up just exactly. This long meter stick, the length will be, we'll write this down in a minute, 200 centimeters. But that goes over to here and makes a pattern on the screen. So right now, if you look in your notes, that slide had 8 different patterns on it that we could shine the laser beam through. And right now, we're shining that laser beam through slide B, pattern B on the slide. And that's a bunch of horizontal lines, and we want to find out how far apart spaced those are eventually. So we're going to collect this data now. And so we're going to measure the distance between that central bright spot and the first spot out using this metric ruler. And that's going to be the distance x. And so we are going to record that as it looks like 1.45 centimeters. So we'll write that data on the board here. And that is data that you need to write down in the data table. So X is 1.45 centimeters. And the length L between the screen and the slide was 200.0 centimeters. In part 4, your objective is to find the relationship between X, the distance between the spot pattern on the screen, and L, the distance from the screen back to the original slide. So here's what we had set up last time. We're at a distance L from the little screen of 200 centimeters. What we're going to do next is we're going to slide in the whole apparatus on this cart and decrease the distance L. And I'm going to film as the distance L gets smaller what happens to the spacing on the screen. So let's slide that in all the way down to a new distance from the screen of 100 centimeters. So let's zoom in on that. And this time, you are going to make the measurement. Okay, so let's go to our data table. And so this is the data that you have already. You've got the new L of 100 centimeters. The original data we took earlier, we had a value of X of 1.45, so you should have recorded the new value of X2. You're going to write that in your data table section for experiment 4. In experiment 5, we're going to be looking at the relationship between little d, the line spacing on the slide, and X, the diffraction pattern spacing, which we've been measuring. So in this particular experiment, we're going to compare what we did in the first experiment, where on the slide, we shine the light through pattern capital B. And this time, we're going to decrease the line spacing on the slide by shining the laser through pattern capital D on the slide. As you can see in this image of what the slide looks like, the lines are more closely spaced. And so we're going to take a measurement in a minute here of what the effect is on X. So if I pan back out, you can see we're now shining the laser through slide pattern capital D. And in our data table, what we want to find out is how does our new X2 compare to X1? So let's take that measurement. Alright, so you should record that measurement and put it in your data table. In experiment 6, we're going to look at the relationship of changing the wavelength of the laser light on the diffraction pattern spacing X. And so we're going to keep all other parameters the same. Our length from the screen to the slide is still 200 centimeters, and we're still shining through pattern capital D on the slide. And so if we look at the apparatus now, the only thing you'll see that I've changed is we put a different laser in, which has a wavelength of 532 nanometers. That's green light. And so on the whiteboard, we have indicated with 2 red dots the pattern spacing caused by a red laser. And you can see the pattern spacing caused by the green laser. So let's go and mark that information down in our notebook. In part 2, the application Seeing Things Too Small to See, what we're going to do is place a different slide in front of a red laser. And that's going to produce a variety of different patterns on the screen, different diffraction patterns. And so your job is to match if you can, 4 given patterns on the slide with the patterns as they're produced on the screen. So we're going to, in sequence here, shine the laser through pattern B, D, F, and E on the unknown slide, and then your job will be to match it with the pattern on the slide that created this. So first pattern here is pattern B. That's what you're looking at right now. So you should record this pattern on your data sheet. And you can pause the video if you need more time to record this, but we're going to slide this over to pattern D on the slide. And so record this data in the pattern D box and make special note of any changes that have occurred in this pattern compared to what you saw in the diffraction pattern produced by B. So next we're going to move over to pattern F on that slide. So make sure you make special note of how this pattern would be different than the other 2 patterns that you saw. So that's pattern F. And then the last one is pattern E. And by the way, when you're looking at these patterns on the screen, you should make special note of the distances between the dots in all directions. Are they evenly spaced or are they unevenly spaced? That's important to make a note of. And so now we're going to go down to pattern E on this slide. And that looks like that. Again, copy this data down into your notebook and make special note of the distances in all directions between the dots. So this is the setup for Kim inquiry number 4, question 10. We have a red laser shining through the slide pattern E, and you can see the data that you're going to collect in the X in the X direction and X in the Y direction. So let's zoom in a little bit and look at the pattern that is making. You can see it's kind of rectangular. The spots aren't evenly spaced up and down and left and right. So the other piece of data that we have here for you is the distance from the slide to the screen, and that's 100.0 centimeters. And I'll just pan around. You can see hopefully that we're set up at 100 centimeters there on that meter stick. All right, so what we'll do is we'll hold a ruler up and zoom in on the pattern, and then you have to record the distances. So let's take that measurement. Here we've zoomed in on the diffraction pattern on the screen, and you need to record the distance from the central bright spot out to the first spot on the right. Make sure you get the right number of significant figures for that meter stick that we're using. It's marked off in tenths of a centimeter, so you're going to estimate 1 place beyond the 10th place. So record that in the data table. Now let's get X in the Y direction. So again, make your best estimate of the distance between the center spot and the first bright spot below. That's X subscripted Y. That goes in your data table. Okay. This is Chem Inquiry 4, question number 11. Measuring the diffraction grating. So here you can see the setup. We've now got a diffraction grating set up in front of the laser, and this is making spots that go left to right. You can see they're quite widely spaced. So we've got a measuring ruler there. We're at a distance L, as you can see, 50.0 centimeters, and I'm going to zoom in, and your job is to measure the distance X. Make sure you get it in millimeters to the correct number of significant figures. So try to walk that in. So in part C, the track spacing in CDs and DVDs, right now we've got the experiment set up for number 15, the CD data. So we're shining that same red laser through a portion of a kind of cracked open CD, and we've peeled off some of the metal. So if you read the background, the CD has sort of a spiral set of grooves in it, sort of like a record, but they're not grooves. They're little indentations called pits that are arranged in a spiral pattern. What you want to find is the distance between those tracks, so to speak, or the distance between the grooves that are etched into that CD. So right now, we've got the red laser shining through the plastic in which those grooves and pits are made in the CD. And if you look on the screen, you can see that there's some widely spaced diffraction spots. And so your job again is to collect this data, noting that L, the distance from the CD to the screen, is 50.0 centimeters. And I'm going to zoom in, and you're going to measure X, the distance from the central spot, which is set at 0 on the ruler, up to that first bright spot up at the top. So let's zoom in and you can collect that data for X. So you should record that to the correct number of significant figures. And make sure when you do your calculation, your track spacing between the grooves on the CD is in micrometers, even though this ruler is marked off in centimeters. So in part C, number 16, we're going to do almost exactly the same thing as we did in part 15 with the CD, except this time we've inserted a broken up DVD into the light path. And we actually had to change the distance L from the DVD to the screen because the spacing that you see for X actually turns out to be quite a bit larger. And so take note of the new spacing L that we've set up here, 34.6 centimeters. And it's very dim to see the first diffraction spot. So what we're going to do is we're going to turn the lights out, and then we're going to make a mark on the board where that diffraction spot is, and then we'll turn the lights back on. I'll zoom in, and you can take a reading of the value of X. So let's lights down. I think you can just barely see that light along the ruler, the little spot. We're going to make a mark on the board there where that is. And then we're going to zoom in. So notice the ruler's upside down, so as you go to the upper left, it's increasing. So we're at least 44 centimeters, and your job is to just zero in and get that reading right where that spot is as closely as you can. Estimate it. Make sure you get the correct number of significant figures. And so that will be your value for X for the DVD. And you'll put that in your data table in millimeters.